Hello and welcome to this last lecture, lecture 9 of module 7. What we have been doing so far is consider several methods for solving initial value problems or for ordinary differential equations. We started off with Runge-Kutta family of methods, talked about the stability analysis, the error analysis for these methods, saw that essentially the implicit methods are much more stable than the explicit methods. Implicit methods are in fact globally stable methods. And then we talked about in the previous couple of lectures some of the advanced techniques for adaptive step sizing and improving the accuracy of the overall numerical solution. And finally, what we discussed in perhaps the last 10 or 15 minutes of the previous lecture was another family of methods called the multi-step methods. Okay, so that is what we are going to discuss in this particular lecture. Okay, so the difference between the Runge-Kutta family of methods and the multi-step methods is this: in the multi-step methods we are going to use the past information, whereas in the Runge-Kutta methods we discarded all the past information and used the information only at yi and ti. Okay, however, in order to reach yi from y0 we have collected information y0, y1, y2 up to yi, and that information can presumably be used in order to one, improve the accuracy of this method, and second, perhaps to improve the stability of these methods. Okay, so what we are trying to solve is the equation of the type dy by dt equal to f of y comma t, starting with y at t0 equal to y0. Okay, and using the chosen method we have somehow reached at time ti, and at time ti we have data at various past values, and this is the time ti. Okay, and we can use the data at this various past values in various different ways, and the two main family of methods that use this particular data is the Adams family of methods and the BDF or backward difference formula based methods. The Adams family of methods they do not use the yi's per se, but they use the function f of yi comma ti. So what you try to do is try to fit a polynomial to the function the past values of fi's. So that means fi minus 1, fi minus 2 up to fi minus n, you fit a polynomial and then you use that particular polynomial instead of f of y comma t. That is what we do in Adams family of methods. As a result of this, the value in Adams family of methods is going to be obtained as yi plus 1 equal to a0 f I plus 1 plus a1 fi plus a2 f I minus 1 and so on up to an f I minus n plus 1. Okay. So this is how we are going to use the Adams methods in order to compute the yi plus 1. What we need to do is find out the coefficients a0, a1, a2 up to an. Now again the Adams family of methods are of two types. A0 equal to 0 is Adam-Bashforth methods, okay, and A0 not equal to 0 is Adam-Moulton's method. Adam-Moulton's is implicit, Adam-Bashforth is explicit. Okay. So these are Adams method. The second set of methods are what is known as backward difference formula, BDF methods, and over there we write yi plus 1 equal to a0 f I plus 1 plus b1 yi plus b2 yi minus 1 and so on up to bn y I minus n plus 1. Okay. This is going to be our backward difference formula. Okay. Now let us look at how to derive this backward difference formula. It is fairly straightforward. What we have is dy by dt equal to f y comma t. We express dy by dt using an appropriate backward numerical differentiation, and that is how we derive the backward difference formula. Okay. So dy by dt computed at I plus 1 is going to be f of yi plus 1 comma ti plus 1. Yi plus 1, keep in mind, is not yet known. Okay. What we can do this, what we can do now is replace with an appropriate numerical derivative. Okay. So the first order backward difference formula, as you might expect, is essentially going to be the implicit implicit Euler's method. Okay. So if we were to replace this with a first order backward difference formula, it is going to be yi plus 1 minus yi divided by h is going to be equal to f I plus 1, which will essentially give us yi plus 1 equal to yi plus h times f of I plus 1. This is nothing but our implicit Euler's method. Okay. So this is the first way, the backward difference formula of order 1. Now if we want to derive the backward difference formula of order 2, we have to replace dy by dt with the numerical derivative of the second order. Okay. What that means is it is going to be equal to yi plus 1 minus 3 yi plus 2 yi minus 1 divided by 2 equal to f of I plus 1 divided by 2h equal to f of I plus 1, and we just rearrange this appropriately in order to get our result for yi plus 1, and this will give us the second order BDF. Okay. Recall that this particular derivative was order h accurate. As a result, the error in first order backward difference formula is of the order of h. This error was, this particular method was order h squared accurate. As a result, the accuracy of the second order backward difference formula is order of h square. We can have third order, fourth order, fifth order backward difference formula, so on and so forth, and we will be able to use an appropriate backward difference formula with an appropriate amount of accuracy. So that's about that's it about backward difference formula. There is one more thing that I will discuss, and that is that the BDF methods, like Adam-Moulton's method or any multi-step method, are non-self starting. What that means, I will come to that in a few minutes. Let us go back, go forward and discuss about how to get derivation for the Adams methods. We will just derive for the Adam-Bashforth method, just one derivation for Adam-Bashforth method would be enough, and I will just talk about Adam-Moulton's method, and we will then talk about this a range of techniques called Adam-Bashforth-Moulton methods of solving these equations. Okay. So derivation for Adam-Bashforth. Okay. At any time ti, what we assume is that the data is available for us for the past n times. That means at any time ti what is available to us is yi comma ti, yi minus 1 comma ti minus 1 and so on up to yi minus n comma ti minus, or sorry, not I minus n, ti minus n plus 1. Okay. So, n past data points, current and past data points we assume are available to us. If yi ti, yi minus 1, ti minus 1 and so on are actually available to us, we can compute fi, fi minus 1, so on and so forth. So, based on this what we will say is essentially fi, fi minus 1, fi minus 2 and so on up to fi minus n plus 1 are known. Okay. So, what we do is we will fit a polynomial to this n past values. What type of polynomial we will fit? We will go back to what we discussed in module 5 and we will fit essentially a Newton's backward difference polynomial. Okay. So, a Newton's backward difference, nth order Newton's backward difference polynomial Pn, we had written this as equal to, sorry, not y, f. Pn computed at location I is going to be equal to fi plus backward difference fi multiplied by alpha plus alpha plus 1 divided by 2 factorial delta squared fi plus so on up to alpha plus 1 alpha plus n minus 1 divided by n factorial delta to the power n fi. Okay. And this is essentially the type of similar type of derivation, if you recall, we had done when we were trying to derive the Newton-Cotes integration formulae also. So, it is the same idea in the Newton-Cotes integration formulae, because all the functions were known to us, we could just use the forward difference formulation or we could of course over there also we could use the backward difference formulation. In this case the values at yi plus 1, I plus 2, I plus 3 and so on are not known to us. As a result we have to use a Newton's backward difference formula, and using this particular Newton's backward difference formula now we have an estimate of what the slope is going to be. Alpha at any time is ti minus t divided by h. Okay. So, at I alpha is going to be equal to 0, at I plus 1 alpha is going to be equal to minus 1. Given the data we will now have fitted, let us assume that we have now fitted a polynomial to the past n points. So, if I plot f versus t, I have this particular polynomial up to the location I. Okay. Keep in mind here I am plotting f and not y. What we will assume is we will extrapolate this particular value of polynomial for this region between I and I plus 1. So, y I plus 1 is going to be nothing but integral from Ti to Ti plus 1 Pn I dt. Okay. So, we have essentially this or rather it is yi plus 1 minus yi is going to be this particular integral. So, we have this particular polynomial that we have just derived, we go from Ti to Ti plus 1, we integrate that with respect to dt. Now, based on this particular equation dt is going to be equal to minus h times d alpha. And note that we are integrating from Ti to Ti plus 1, Ti represents 0, Ti plus 1 equal to minus 1. So, the limits of integration are going to be from 0 to minus 1, and we can substitute alpha equal to minus alpha and redo and solve this particular derivation, and we will be able to get yi plus 1 is going to be equal to yi plus integral from 0 to 1 Pn of I dt. No matter what value of n we choose, the limits of integration are going to remain from 0 to 1. I am sorry, this should not be t, it should be actually alpha. Okay. So, now let us look at the first order Adam-Bashford method. First order Adam-Bashford method is going to lead us to nothing but the Euler's explicit method. So, first order Adam-Bashford method basically is going to be that we will be left only with Fi, okay, and if that means we are only going to use one previous point Fi, okay. So, if we were to put this over here, what we are going to get is yi plus 1 equal to yi plus h multiplied by so this should be h d alpha. When we replace dt is going to be h d alpha, and that is where this h comes from 0 to 1 is going to be fi multiplied by d alpha, which is going to lead us to yi plus h times fi, okay. So, this is going to be our first order Adam-Bashford method. So, n equal to 1 Adam-Bashford method is nothing but the Euler's method. The beauty about all these derivations that we have seen so far is the first order Runge-Kutta method reduces to nothing but the Euler's method of the explicit Euler's method. The BDF formula of first order reduces to implicit Euler's method. Adam-Bashford method reduces to, for n equal to 1, reduces to nothing but the explicit Euler's method. Likewise, the Adam-Moulton's method, which we will not do the derivation for in this lecture, is going to reduce to nothing but the implicit Euler's method. And the second order Adam-Bashford method, if we go on to this particular type of a formula, second order Adam-Bashford method is going to use Fi and Fi minus 1. When it uses Fi and Fi minus 1 in this particular polynomial that we have, we will be left with these two terms, okay. So, for the second order Bashford method, the derivation is going to be yi plus 1 equal to yi plus h times integral from 0 to 1 P2 actually it should be P1I d alpha based on the notations that we have been using consistently since module 6, okay. P1I is nothing but Fi plus alpha times delta Fi, which is nothing but Fi plus alpha times Fi minus 1, okay. So, we substitute this over here and integrate, we will get yi plus 1 equal to yi plus h multiplied by Fi alpha plus Fi multiplied by alpha square by 2 minus Fi multiplied by alpha square by 2 going from 0 to 1, okay. So, this will reduce to Fi multiplied by 1 minus 0, which is going to be Fi. This is going to be nothing but Fi multiplied by half minus 0, that is going to be plus half Fi, and this is going to be Fi multiplied by 1 by 2 minus 0, that is going to be half times, sorry, Fi minus 1, that is going to be I minus 1 multiplied by half, and that is a negative sign over here. So, it is half F I minus 1, okay, multiplied by h plus yi, okay, and finally our result is going to be yi plus 1 equal to yi plus h times 3 by 2 fi minus 1 by 2 fi minus 1. This is Adam-Bashforth method of order 2. And in deriving third order Adam-Bashforth method, we are going to say yi plus 1 equal to yi plus h times, again integral from 0 to 1 p2 of I multiplied by d alpha. Now p2, if we go back over there, p2 is going to be fi plus alpha times del fi plus alpha plus 1 del square fi. So this is going to be fi plus alpha del fi plus alpha square plus alpha by 2 del square fi d alpha, which is going to be equal to yi plus h fi alpha. So now we are just integrating this, there is no alpha over here, so it is going to be fi alpha plus del fi alpha square by 2 plus del square fi by 2 factorial multiplied by integral of alpha square d alpha, that is going to be alpha cube by 3 plus del square by 2 factorial alpha square by 2, alpha going from 0 to 1, okay, and that we will be able to write as yi plus h. Since alpha goes from 0 to 1, the difference is just going to be equal to, this is going to be 1, this will be replaced by 1, this will be replaced by 1, and this also will be replaced by 1. So we will have fi multiplied by 1 plus del fi is nothing but fi minus 1, fi minus 1 multiplied by half plus del square fi, if we recall, it is fi minus 2 times fi minus 1 plus fi minus 2 okay, divided by so this is going to be multiplied by, this entire term is going to be multiplied by 1 by 6 plus 1 by 4. Okay, so that is going to be yi plus h times 3 by 2 fi minus 1 by 2 fi minus 1 plus this term is going to be 4 plus 6, 10 by 24, 10 by 24 is 5 by 12 plus 5 by 12 fi minus 2 multiplied by 5 by 12, that is 5 by 6 fi minus 1 plus 5 by 12 fi minus 2. Okay, and this finally will lead us to yi plus h multiplied by 3 by 2 plus 5 by 12. So that is 18 by 12. So 18 plus 5 is 23. 23 by 12 fi minus half plus 5 by 6, that is going to be 3 by 6 plus 5 by 6, that is going to be 8 by 6. So that will be 4 by 3 fi minus 1 plus 5 by 12 fi minus 2, and this is going to be our Adam-Bashforth third order method. Okay. So, this is the results for Adam-Bashford third order method. For a fourth order method, in addition to this, we will have alpha, alpha plus 1, alpha plus 2 divided by 3 factorial multiplied by del square fi over here. We will do that integration, we will do the substitution, and we will get a fourth order, fifth order, sixth order and higher order Adam-Bashford method. Now, what is the accuracy of nth order Adam-Bashford method? If we go back and see what the errors are going to be for this, so let us go back and look at the polynomial expression for an nth order polynomial expression for Pn. The error is of the order of h to the power n plus 1. Okay. So, now if we substitute that over here, okay, an nth order Adam-Bashford method uses P n minus 1. Okay. So, an nth order Adam-Bashford method, because it uses P n minus 1, the order of accuracy of the polynomial used in nth order Adam-Bashford method is h to the power n. Okay. And now there is this h term that comes in over there, which makes the nth order Adam-Bashford method, the local truncation error of that is going to be h to the power n plus 1. Okay. I will write down what I have said over here. For n equal to 3, for n equal to 3, yi plus 1 equal to yi plus integral from 0 to 1 P2 h d alpha. Okay. Now, for P2 the accuracy is of the order of h cubed. Okay. This is what we had derived when we talked about the backward difference, Newton's backward difference interpolating polynomials in module 6. Okay. And then there is this h term that comes over here. So, h multiplied by a number that is order of h cube accurate becomes order of h to the power 4 accurate. Okay. As a result, Adam-Bashford method of order 3 has a local truncation error of h to the power 4, and the global truncation error is going to be of the order of h to the power 3. Okay. And that will work for any nth order Adam-Bashford method. As the order of the Adam-Bashford method increases, the accuracy also tends to increase. Okay. So, ABN accuracy for the global truncation error is going to be of the order h to the power n for global truncation error. Okay. So, that is the result for Adam-Bashford method. What we do in Adam-Moulton's method is the same thing, but we will have to get the polynomials which involve f I plus 1 also, because what we are trying to do in the Adam-Moulton's method is we also have the f I plus 1 term. So, in the first order Adam-Moulton's method we have f I plus 1 and f I. Second order Adam-Moulton's method f I plus 1, f I minus 1, so on and so forth. We fit an appropriate size polynomial and then proceed in exactly the same manner as we did for the Adam-Bashford's method. Okay. I will not go over the derivation of the Adam-Moulton's method, but now I will talk about some practical issues in implementation of Adam-Bashford's method, or in general for any of the multi-step method. So, we start off with dy by dt equal to f starting from y0 at t0. Okay. Now when we start, let us consider the Adam-Bashford third order method. Okay. So yi plus 1 for Adam-Bashford third order method is going to be yi plus a1 fi plus a2 fi minus 1 plus a3 fi minus 2, where if we go back to this particular derivation, a1 is 23 by 12, a2 is minus 4 by 3 and a3 is 5 by 12. Okay. So these are the values of coefficients that we can use in this particular Adam-Bashford formula. Okay. So this is the overall Adam-Bashford formula. At I equal to 0, the formula is going to be yi plus 1 equal to yi plus a1 or y1 equal to y0 plus a1 f0 plus a2 f minus 1 plus a3 f minus 2. F minus 1 is f computed at y minus 1 comma t minus 1, and this is at y minus 2 and t minus 2. Okay. Keep in mind that we know the value at y0, we do not know the value at y minus 1, we do not know the value at y minus 2. So at I equal to 0, Adam-Bashford method cannot be used. Let us see what happens at I equal to 1. At I equal to 1, y2 is going to be equal to y1 plus a1 f1 plus a2 f0 plus a3 f minus 1. Again f minus 1 is not known to us. If f minus 1 is not known to us, we cannot use Adam-Bashford method at I equal to 1 either. Okay. At I equal to 2, what happens? Y at I equal to 2, y3 is going to be equal to y2 plus a1 f2 plus a2 f1 plus a3 f0. Now from starting from I equal to 2, we can actually use Adam-Bashford third order methods. So Adam-Bashford nth order methods can be used to compute yn onwards. It cannot be used to compute y0, y1 and so on up to yn minus 1. Okay. So this is what is known as, these methods are non self starting. Okay. So when we are at y0, we cannot use Adam-Bashford method. When we are at y1, we cannot use Adam-Bashford method. When we are at y2, we cannot use Adam-Bashford method. From y3 onwards, we can start using the Adam-Bashford third order method. So what is the solution? There are various ways to do. One is you can use the Euler's method to compute y1. You can use Adam-Bashford second order method to compute y2, and so on. You can use Adam-Bashford third order method to compute y3 and all the future y's. Okay. So this is one possibility. Now the problem with this is the Euler's method is h square accurate, Adam-Bashford second order method is h cubed accurate. So we are losing on the accuracy. So these are again the local truncation errors. We are losing on the accuracy by using the less accurate methods in order to start this particular system. The second possibility is to use the self starting methods such as the Runge-Kutta method. and the RK method of the same accuracy that we can use is essentially the RK3 method. RK3 method will be used to compute y1 and y2, okay, and Adam-Bashforth 3 method will be used to compute y3, y4 and so on. Okay. So these are the two possibilities that we can use that we can implement in order to use the Adam-Bashforth's non-self starting methods. Okay. So this is one of the issues that the multi-step methods faces. Is not just the issue with Adam-Bashforth method, it is issue with all the three methods, Adam-Bashforth's, Adam-Moulton's and the backward difference formula method, and these are the ways to handle them. Of these two ways, this is typically the preferred way. It is preferred really because you can maintain the same level of accuracy for very stiff problems and for problems in which the lambda values are very high. Under those conditions, what happens with the RK method essentially is that you need to use really small step sizes in order to get good solution from the RK method, but other than that, this is essentially the procedure that is going to be used in order to use the non self starting methods. Okay. Now when it comes to implementing the Adam-Moulton's method, we will have the same practical issues as the Adam-Bashforth method. There is one more challenge to it, and that is these equations are written, the AM4 is going to be written implicitly, or sorry, AM3 will be written in the form of yi plus 1 is going to be equal to yi plus a1 a0 f I plus 1 plus a1 f I plus a2 f I minus 1 plus a3 f I minus 2. Okay. So now this yi plus this f I plus 1 depends on yi plus 1, making this an implicit scheme. So we have this nonlinear equation which we need to solve in order at each time interval in order to get the Adam-Moulton's method. Okay. And finally we come to the last technique, and that is known as Adam-Bashforth Moulton method, and the relationship between Adam-Moulton and Adam-Bashforth method is the same as the relationship between the predictor corrector Yoon's method and the implicit Crank-Nicholson method. That is, in implicit Crank-Nicholson method we need to solve this equation repeatedly until the conversion is reached. On the other hand, in the predictor corrector method, what we do is we use a predictor equation, and this particular equation is used as an expression that ends up being the corrector equation. So what we do is in Adam-Bashforth Moulton method is first use ABN to obtain y I plus 1 0. So the Adam-Bashforth method is used as a predictor, and next you use AMN as an expression to get y I plus 1 1, y I plus 1 2 and so on up to y I plus 1 m. So we repeat the corrector equation a fixed m number of times in order to get an improved solution using the Adam-Moulton's method. So Adam-Bashford-Moulton's method is a predictor corrector method. Okay, where the Adam-Bashford is used as a predictor and Adam-Moulton is used as corrector. Okay. So okay, that essentially finishes the what I wanted to cover in module 7. What I will now do is spend the next 8 to 10 minutes recapping everything that we have managed to cover in this particular module. So now what I am going to do is spend the next few minutes recapping what we have done in the last 9 lectures in for the numerical methods for solving the ordinary differential equation initial value problem. Okay, we started off with an example of the plug flow reactor. What we said is that for a straightforward single reaction system, we have the design equation for the plug flow reactor, where the volume of the plug flow reactor is going to be given by area under the curve. For the specific example that we took, the volume of the PFR was computed by area under the curve 2 divided by c to the power 1.25. Okay, and this area gave us the total volume of the PFR required to reach a certain conversion x. What we said was that this particular design equation is obtained from this particular ordinary differential equation, and then we recast the overall problem as a problem of solving the ordinary differential equation given the initial concentration C at volume V equal to 0. Okay, and the entire lecture series, all the 9 lectures in this particular module, what we have done is we have used this example in order to compare the various methods, contrast the various methods, and try to prove essentially some of the things that we were interested in knowing in this particular method. Okay. Now let me just talk about the geometric interpretation. We have covered geometric interpretation multiple number of times. What we do in any kind of an ODE solving technique is yi plus 1 is given as yi plus h times certain slope. Now this slope in Euler's explicit method is nothing but the slope computed at Ci comma Vi. In Euler's implicit method is nothing but the slope computed at Ci plus 1 comma Vi plus 1. In Runge-Kutta method we use multiple points between Ti and Ti plus 1, in this particular case between Vi and Vi plus 1. Okay. So nth order Runge-Kutta method uses slope computed at n points between I and I plus 1, both these points may be inclusive, and the final slope is nothing but the weighted average of these values. Okay. What I am showing over here is RK2 Yoon's method. Okay, in Yoon's method what we do is this particular red arrow is the slope computed at Ti Ci comma Vi. Okay, based on the slope computed as Ci comma Vi, we project at this particular point. Note that this is not Ci plus 1, this is just the projection of Ci at Vi plus 1 using the slope at Vi. Okay. So this is the projection, we compute the slope over here, the slope is shown by this particular dotted line, the slope of this line and slope of this particular arrow is the same, and the average of these two slopes is the actual slope shown by this black line. We use this slope in order to get Ci plus 1 in the Yoon's method. Okay. Then we took up the geometric interpretation of 4th order Runge-Kutta method. The classical 4th order Runge-Kutta method use slope at Vi, then use slope at Vi plus half, use slope at Vi plus half, then use slope at the improved value of Vi plus half, and then use the slope at Vi plus 1. Okay. So we had those 4 slopes, this black line, red line, blue line and this green line, and the final slope was nothing but the weighted average of all these 4 lines. Okay, that was RK4. Let us go back one more slide and just talk about the Yoon's method again. Yoon's method computes the slope at Vi, computes the slope at projected value of Ci plus 1 at Vi plus 1, not the actual value of Ci plus 1 at Vi plus 1. The predictor corrector method again does the similar things, but in an iterative way. What we do is, this red arrow is nothing but the predicted value Ci plus 1. This predicted value of Ci plus 1 is used to compute the new predicted value of the new corrected value of Ci plus 1 first time. This slope at Ci plus 1 is used to get the average again, Ci plus 1 2, so on and so forth. We use this particular prediction and correction multiple number of times in order to finally get Ci plus 1. And then we talked about Crank-Nicolson method. The idea of the Crank-Nicolson method is that this is, the red line represents the slope at Vi comma Ci. This dotted line represents the slope at the final solution, which is yet unknown, because it is the true solution at I plus 1. It is the slope at true solution at I plus 1. This is an implicit method. Why it is an implicit method? Because this true solution at I plus 1 is not known at time I. So, we need to compute both Ci I plus 1 as well as the slope at Ci plus 1 simultaneously. Okay. That is the Crank-Nicolson method. So, this actual slope in the Crank-Nicolson method is the weighted average of the slope computed at Vi and the actual slope computed at Vi plus 1. Okay. Being an implicit method, it is a globally stable method. Okay. So, this is all we covered in the Runge-Kutta family of methods, and let us talk about the summary of all these methods. What I am showing over here is the method, the number of points between I and I plus 1 that is used, whether it is self starting or not, the global truncation error and general comments. Euler's and Euler's implicit method both use only one point. Euler's method uses the point at I, Euler's implicit method uses the point at I plus 1. The global truncation error in both the cases is order of h to the power 1 accurate. Euler's method is very easy to implement. Euler's implicit method is difficult to implement, but it is globally stable. Yoon's method is kind of like trapezoidal method. It is not exactly like trapezoidal method, it is kind of like trapezoidal method. The Yoon's predictor corrector method is much more like a trapezoidal method. The corrector equation is indeed a trapezoidal method. Yoon's method uses 2 points and therefore it is an RK2 method. Midpoint method uses is also an RK2 method, and the RK-Gill method is an RK4 method, and the global truncation error for second order Runge-Kutta method is h squared, and for the Runge-Kutta-Gill's method is h to the power 4. Okay. A general comment is, if you do not have any idea of what ODE solver to use, your first choice should be a fourth order Runge-Kutta explicit method. If you know a priori that the system is very stiff, in that case go ahead and use implicit methods, but if stiffness is not an issue, then you can go ahead and use the RK4 method as your first choice. A lot of RK4 methods are now available. If you go to netlib, NETLIB, that stands for network library, netlib.org, you will have a lot of ODE solver techniques that you will be able to download for Fortran. For MATLAB, essentially you can use ODE 45, which is a fourth order, fifth order Runge-Kutta cache-carp method. Okay, then we talked about just a few slides earlier, we have talked about comparison of the second order methods. The RK2 variant of Yoon's method is what we had just discussed over here. The predictor corrector form of Yoon's method can be order h square accurate or h cube accurate, I will come to that in a minute, and the Crank-Nicolson method is an implicit method and therefore it is stable and it is h square accurate. Probably the two most popular methods for solving ODEs are the RK4 method, which is an explicit method, and Crank-Nicolson method, which is an implicit method. These in my experience are perhaps the two most popular methods for solving ODE initial value problems. Okay. And then in essentially in today's lecture we covered what is known as the multi-point methods, and an example of a multi-point method is the Yoon's predictor corrector. Indeed, Yoon's predictor corrector method is an Adam-Bashforth-Moulton method of second order. The Yoon's predictor corrector method is a non self-starting method which has a global truncation error of h cubed. How it is different from multi-point from the original predictor corrector Yoon's method is that in the predictor corrector Yoon's method we use essentially the Euler's method in order to compute the predictor equation. If we go back to this particular slide, what we do is at this particular point we use Euler's method to project the point in the future. So the first method is going to be h squared accurate, that is the Euler's method. Instead we can replace the Euler's method by a trapezoidal like method, and that will give us the multi-point predictor corrector Yoon's method, okay, and that is h cubed accurate. The Adam-Moulton's method which takes 4 points is h to the power 4 accurate. I am sorry, there is an error over here, this should be h to the power 4, and the fourth order Adam-Bashforth method is an implicit method which is again h to the power 4 accurate. We also talked about the backward difference methods. Backward difference methods are much more simpler to use than any of the other methods that we have talked about, any of the other implicit methods that we have talked about, except of course the implicit Euler's method. So backward difference methods are also popular in what is known as differential algebraic equations. This is just something that that's for information, and if you do not understand the previous statement you can of course ignore it. And then finally what we have also done is covered the advanced techniques. We just talked about stiff systems. If the ratio between the largest and the smallest eigenvalue in your system is greater than 10 to the power 5, do not even think about it, just go and use implicit methods. The specific implicit method that I can suggest to you are either the Adam-Bashforth method or the Crank-Nicolson method. You have the choice to use one of the two. In MATLAB we have ODE 15S that solves a stiff system of equation. The other thing we talked about is Richardson's method in order to improve the accuracy. It is the same idea as we have covered in the numerical integration section of this particular course. And finally the adaptive step sizing, and in adaptive step sizing for RK4 method the step size h scales as delta to the power 0.2. Likewise in fourth order Adam-Moulton's or Adam-Bashforth method h scales as delta to the power 0.2. And we have the Adam-Bashforth-Moulton's predictor corrector method that can be used instead of the Adam-Moulton's implicit method, okay. So in summary, if you have to use an ODE solver, try to use the fourth order RK method with adaptive step sizing as your first choice. If that does not work, try to use your Crank-Nicolson method. If you need a higher accuracy compared to what Crank-Nicolson method is going to provide you, you may either use the Adam-Moulton's method or backward difference fifth order or fourth order methods in order to get a higher set of accuracy. With this we end module 7 of our course, and I will see you again in module 8 where we are going to discuss ordinary differential equations boundary value problems. Thanks.